Video I am going to describe the IV characteristic of a silicon diode junction. This is the IV relationship of a silicon diode. There are three parts in this graph. From this region to this is the forward bias region. From 0 to the minus VZK, this region is the reverse bias region, and below minus VZK it is the breakdown region. We can see from the graph that up to 0 to 0.5 voltage the current I is approximate to 0. That says it is there is a very little current in this region, and this region is called the cut in, and this voltage is called the cut in voltage. And above the 0.5 voltage, we can say from 0.6 to 0.8 voltage the current increases dramatically, and the current and the graph becomes like an exponential graph. So we can say that at 0.7 voltage the current I increases, and this tells us that in this region the relation between the I and V is an exponential relation. So we can say that I is equal to Is into e to the power V by Vt minus 1. This is the relation in the forward bias region of a silicon diode. Here I is the current, and Is is the saturation current. It is also called a scale current because it depends on the area of the diode. That is, if the area increases, it will also increase, and it also depends on the temperature. And actually in the room temperature we take it as 10 to the power minus 15 ampere, and if we rise the temperature by 5 degrees Celsius, the Is doubles. And next we can say Vt. It is the thermal voltage. At room temperature, that is, we can take 20 degrees Celsius, it is 25 millivolt, and we can say we can find it by Kt by Q, and in this equation K is the Boltzmann constant, T is absolute, temperature, Q is charge. So this is the this is the characteristic curve and characteristic curve. Then next we can move to another relationship. That is, if we say I1 is equal to Is into e to the power V1 by Vt, then I2 is equal to Is e to the power V2 by Vt. Then 2 by 1 is equal to I2 by I1 is e to the power V2 minus V1 by Vt, and we can take logarithmic scale. Ln I2 by I1 is equal to V2 minus V1 by Vt. So V2 minus V1 is equal to Vt into ln I2 by I1. This is another equation, and this comes to the end of the forward bias region, and there is and we can next move to the reverse region, that is from 0 to minus VZK. In this region the I goes to the negative side, and in this region the exponential relationship, that is in the forward region we found that I is equal to Is into e to the power V by Vt, and in this case -1 is very much little and I is much bigger than Is, so we can take it I is equal to Is e to the power V by Vt. So this is the forward region relationship, and in the breakdown in the reverse biased region, and the exponential term becomes to unity, comes to approximate unity, that is I is actually approximate to minus Is, that it becomes approximate equal to the saturation current, but it is in the negative region, and as the saturation current is constant and it depends on the temperature only, that I also becomes approximate constant. That's why we can see that I is approximately constant in this region, but at minus VZK the I increases in the negative region, that is in the minus VZK this increases in the negative region, and that's why the it also and that's why it also goes in the negative region, and it is breakdown voltage. In this region there is a breakdown, and in this is called the breakdown voltage, and we can say VZK. Here Z signifies the Zener, and K is the knee. K is the knee region, that's why it is called minus VZK. So this is the term, this is the graphical description of the characteristic of a silicon junction diode.